Okay, everybody, so we are going to take a quick look at chapters 2 and 4 out of Bettinger. And this is going to be primarily looking at some of the stand conditions that you are going to be looking at when you go out into the field. And then we also spend a little bit of time talking about the differences between even-aged and uneven-aged stand management. I'm going to scroll through the chapters as we go along here and just point out some of the things that I think are of importance when we're taking a look at this. Now, chapter 2 has a lot of information in it. We're going to be focusing primarily in this lecture right here on really on just goal number 1 there, understanding the plethora of biological measures available for evaluating construction or structural conditions of a forest before and after planned management activities. That allows us, basically it's the measurements that we can have at our fingertips that allow us to describe these stands. A little bit later we'll be looking at estimating some of the financial ways of describing a forest too. They're perfectly good ways of describing the forest in terms of future or present values, and then also looking at some of the financial formulas used in decision making down the road. So again, this book kind of explores some of the things that we've covered over the past year and a half in forest measurements and insuration. And so some of the things that we collect data on give us information such as a density estimate, trees per unit area, average diameters of trees, and of course they list all the different ways that, or all the rules that we've all talked about in terms of measuring tree diameters. Those are very important criteria. When you're working with trees per acre, you can look at it in a couple of different ways. One is to develop what we created in class, just your standard stand table. Okay, and a stand table is basically for every diameter class you come up with an estimate based on your sample of the trees per acre. And here, of course, they're showing the trees per hectare as well. So you could also look at it in graphic format here, and I'm trying to determine which one of these two stands. These are two different stands, one at age 35 and one at age 110. They have a very different stand diameter distributions. I think what we're looking at here is this even age stand, age 35. So something that they point out is your stand distribution table or your diameter distribution tables. When you look at them in graphic format, they really tell you a lot about what's going on. It's a little bit better to view this information in a table format. You can see the real difference between the age 35 and age 110 even-aged stand diameter distributions. They both are even-aged stands, but you can see with the younger stand that the majority of the stems, there's a lot more stems per acre, first of all, if you add them all up. And then the majority of those stems are in the smaller diameter classes with a much tighter curve around each side. There's a lot less variation in those from what would be around the average diameter. There's a lot less variation, so you have a much tighter bell-shaped curve. As it gets older, things start spreading out more. You end up with a lot more variation in that stand, and you're starting to get perhaps even some younger stuff trying to move in. But basically what you end up with is this really widely spread out bell-shaped curve. And and it's shifted. The average diameter is shifted to the right. Okay, so you have a lot less trees per acre if you add them all up, plus the average diameter is considerably larger than you see on the even-aged stand. So that's the diameter distribution of an even-aged stand, and as we learned briefly, we didn't spend a whole lot of time talking about it, but the stand diameter distribution of an uneven aged stand looks more like this. And they're actually kind of showing you in essence what I showed you a little bit in class, that you could have little clumps of smaller even aged stands that make up this uneven aged stand. So that's something important to be aware of. We're going to explore this curve here a little bit later. In fact, I've taken I believe the data for this curve, and I have will be using this to show us how we can create our own curves and manage our uneven age stands based on these J-shaped curves. Okay, so stay tuned for that. So looking a little further down the book here, we see another very, very, very important density estimate, this basal area. And it kind of just describes, again, for the umpteenth thousandth time, what basal area is. Okay. If you scroll down a little bit further, it gives you the formulas that we use, and obviously, basically it's deriving that formula that we all know and love in class here. Okay. If you want to see it on the metric version, then you basically would be using this formula down here, where your dBH is measured in centimeters, and you square that and multiply it by this magic number, and it gives you the basal area in square meters. Right, so something that the basal area and the trees per acre can give us is this estimate that is used by foresters and is really liked, and it's basically this quadratic mean formula. And we actually learned how to calculate that in forest mensuration last summer. We went through this step here. We also went through it in the silviculture class, and we used a formula that looked kind of similar to this. Basically, you take the basal area per acre, divide it by the trees per acre, divide that by 0.005454, and then take the square root of it. And what it gives you is this estimate that is preferred by foresters, because I think it takes out a lot of the variation that you would see in a natural stand. And so it gives an estimate of what the average diameter is that is, like I said, is preferred for modeling stands and those sorts of things. Average height is another important estimate, and it helps people when they're reading your report to help visualize what's going on out there. I not only get the average height, I will also get the height of the range of the heights as well. I think that's a pretty important thing, especially on an even aged stand. And of course, height is definitely related to site index. And of course, you only want to do the dominant and co-dominant trees. Okay, so we'll get to that just a little bit. Timber volume is also obviously a very, very important way of describing the stand out there. And one of the things that it does tell us eventually is that stand at any kind of a point where we might be able to do any harvesting in it. Okay, and so between the actual volume that we have out there and the stand diameters, that lets us know how much we have and what product classes we have with those. Okay? And of course, that can be translated into the value in terms of if we're trying to sell it, which may or may not make or break a management decision for us. Okay, well, that brings us to the mean annual increment, periodic annual increment, and we've kind of talked about this in silviculture. It was one of the later topics in the class, MAI and PAI. And one of the things that this works for the most is really on even age stand management. It's really a good way of determining when it might be economically the point at which you reach biological maturity, and once it reaches this point of biological maturity, you may be wanting to think about, should I be doing something out there? Maybe I'm going to be, maybe I need to be thinning it, or maybe I need to be looking at a rotation on it as well. So again, the periodic annual increment is basically taken. In this case, it's on a 5-year annual increment. They just look at the change of volume every 5 years. So the volume's been changing by this much between 20 and 25 years, and this much between 30 and 25 years. It's just charting that difference between the volume at age 40 and the volume at age 45, okay, for instance, and it just plots that out. The per acre volume obviously just keeps growing, all right? So that never stops until a harvest takes place. So so I was differentiating in class the differences between the current annual increment, or what they also call the mean annual increment, and the periodic annual increment. Okay, so really what that is, this estimate is just the volume of a tree at a particular age. So what is the volume of this stand at age 10? That's plotted, and that's on a per acre basis. And then what is the volume of that stand on a per acre basis at year 15? And so just every period, time period that you're looking at, you're just finding what the average volume is. The periodic annual increment, like I said, is the difference between the two periods. So while MAI, mean annual increment, is taking the total volume and dividing it by year 10, all right, and then doing it again at year 20. What PAI is doing is it's taking that difference between year 15 and year 10, subtracting year 10 from it, and it's plotting that out for you. So the periodic annual increment goes up, and it peaks pretty young in age. The mean annual increment peaks pretty close to what we might consider the biological peak of the stand, and then the growth rate starts to slow down over time. But it's a little hard to tell exactly where that peak is. So what foresters have devised is when the PAI comes down and crosses over the MAI, that seems to be a really good place financially and otherwise to think about maybe doing the rotation of that stand. So some other estimates that we really like to use in forestry a lot too, that really help describe what's going on, are things such as some of the dead woody material that's out there. Snags represent homes for and habitat for a lot of woodland creatures, and so maintaining a certain number of snags per acre may be a mandate. In fact, the Forest Service, I forget what the U.S. Forest Service has a requirement of snags per acre, and I don't recall exactly what that is. Seems to me it was like 5 snags per acre or something along those lines that were needed to be left after a clear cut. So actually managing or monitoring that and taking estimates of that while you are out in the field is not a bad idea. Okay, so for instance, if you're going out and you're doing your 10 early assessment plots, that may be a good time for you to actually mark down how many snags per area, per unit area you think you're seeing out there. Downwoody debris is another important one. This estimate is used not only for describing types of habitat, salamander habitat, and other things, but it's also pretty important when you were looking at fire risk estimation. So downwoody debris directly relates to fuel loads and those sorts of things that you have out there in the woods. So, and it may be that the group that you're working for has a real interest in knowing what that might be. If they're trying to do some fuel reduction type work. Canopy cover is another one that I like to try to at least give a kind of a ballpark estimate. We have little tools that actually will give us an estimate of the percent crown closure. You stand under it and you look through a mirror and you guesstimate what percentage of clear sky you can see through the stand. And I could show you one in class. I'll remind me on Thursday, and I'll bring one in. So, it's pretty important because it allows you to estimate a lot of things. One is, as we all know, leaves make trees, right? So if you have a completely closed canopy, your leaf area index is probably considerably higher, which means that the trees are probably getting a lot of sunlight, or there's a lot of sugar making factories there. Okay, however, it could be too dense. So considering the species, the other thing that's important is you may be trying to open the site up for wildlife, and being able to get that canopy cover thinned back a little bit might be an objective that you're trying to do. It could be for like I said, wildlife habitat, or it could be for oak seedling regeneration and establishment, those sorts of things. So anyway, that's it does help us to identify and kind of guesstimate a little bit how much light is making its way down through the canopy. Tree stand or forage age is obviously a vital piece of information for us. The tree age tells us a lot about where the tree is and where the stand is in terms of how the stand originated. Was it even age stand? Was it done in small groups or individual trees? Was there small, is it, as we say, kind of the steady state system where you might see an all age stand? Those sorts of things are very important. Other things where stand age is extremely important is, are we nearing the end of a rotation age for a specific tree based on its biological maturity? And then, of course, the other is an estimate of the site index, where we use the stand age or the tree age or the canopy, or the dominance and codominance, and we compare that against their height, and that gives us some sort of an idea as how productive the site is. So a lot of good reasons to get stand age, which obviously is something you're going to be collecting while you're out there. So, and of course, this section goes into the differences between even age and uneven age stands. And again, it shows you the distributions for these. What's kind of interesting is that we often do not, when we're talking about even age and uneven age stands, we often do not plot on the x-axis the actual age, which is what they have here. They're showing you these various age classes in 5-year increments. But what we tend to do, if you all remember, is we tend to plot diameter. We use diameter as a surrogate for age a lot of times. And so that's just something to bear in mind, because it's a lot easier to go out and measure a bunch of diameters than it is, obviously, to measure a bunch of ages. And just bear that in mind, that, even though we use those terms all the time, the actual metric that we use is typically diameter. And of course, we do plug age in there. We will go out and collect some data on ages as well. So in the advent of the burgeoning carbon markets that we have, and hopefully that will be something that we can see further on down the road, where we see forest carbon sequestration credits for landowners. Obviously, an estimate of carbon in the stand, and not only the existing carbon in the stand, but how much carbon is being put on every year by a stand is of vital importance. And they show you this big formula right here, and this is really the scientific mathematical way of doing it. Essentially, though, if you take the cubic foot volume of a tree and multiply it by more or less 65 pounds, okay, per cubic foot, and then divide that by 4. That'll give you the pounds of carbon that are in the tree. Okay, and so this is probably smarter using this. It kind of keeps you straight, but essentially, you take a tree and half of its weight is in water. If you subtract that out, that gives you half of the dry wood, or that gives you the weight of the dry wood. Half of the weight of the dry wood is essentially pure carbon. So whatever the weight of the dry wood is, you just divide that by 2, and you've got the amount of carbon. So they're running through this formula, and essentially 2,500 cubic feet of wood per acre translates to about 18. So when it translates into 36,660 pounds per acre. Divide that by 2,000, and that gives you tons per acre. And we deal with carbon on the per ton basis. So then you go back the next year, and you find you've got 2,600 cubic feet out there. You run it through the same formula, and essentially what you find is that next year you've got 19.43 tons per acre, or you have added 1.1 ton per acre, okay, over that time period. So again, you can look at that, and you can estimate based on current growth rates what you think that might be putting on down the road. You could model those sorts of things. So another important commodity that we're starting to see, besides just growing carbon and growing timber, is also down in the southeast. Most of you all got to see pine straw production, and here in North Carolina, it's primarily longleaf pine. You go to Georgia, parts of South Carolina, slash pine is the preferred species. It just grows better there. So one of the things that they did point out is, depending on how productive your stand is, you can, within a fairly early time period, about 15 years, you could start getting a lot of pounds per acre. That's 1.5 to 2 tons of pine straw per year. Okay, that leads into, I think they're about, let me see if I can remember that. I don't really recall the weight of a bale. I think if you assume they're about 10 pounds, then you may get about 200 bales per acre. Okay, somewhere in that range on a really, really good stand. And depending on how that straw is raked up, we saw hand raking down east, and they will pay about somewhere about anywhere between 25 cents to $1 per bale. So a landowner could make $60 to $80 per acre. Okay, and when they're doing basically hand raking, how easy it is to access it and how close the markets are and all that good stuff. So, all right, so. Then there's other non-timber forest products. I'm still waiting to hear back from our good friend down at the mountain research farm, the Mills River, and she'll be. I'm sure we'll work it out with her, and we'll be able to meet with Janine Davis and take a look at some of the other commodities that you can actually get. But there are a lot of biological, medicinal, and spiritual materials that can be gleaned from the forest, and so again, that's something that is of importance too. So you can make some sort of a estimate while you're out there, and they give you I'm not a mushroom expert. I will end up killing myself or the people around me. But if you are good at that, you might be able to come up with some sort of an estimate of mushroom production out there, current mushroom productivity, and then of course improving the opportunities for landowners. So that will be something that you might be able to look at. And so then of course site quality is an important one as well. And Bettinger spends a lot of time describing what are some of the more formally used site quality estimates, and of course we're all familiar with site indices and what site index means. Poor sites, you probably do not want to focus a lot of your management on poorer sites simply because you're not going to get as good bang for your buck. That's essentially the bottom line. So you divert your focus to those sites that you know that you're going to be getting some good quality results. Whereas you can devote your poor sites to other things such as recreation and good wildlife habitat. Because just because it's not the best for growing trees doesn't mean you can't have really good, high quality wildlife habitat there as well. And cover and those sorts of things. So it gets into a lot of detail about site indices. Not going to worry about it too much. It just wants you again to be aware of how we use site index and how we estimate it and what we use that for. And I think you all probably got a pretty good handle on it. But again, that's something that you want to just bear in mind, that that's a major importance. Then we get into site quality and stocking and density. So again, those two estimates that we were using in the field were trees per acre and basal area per acre, how we could plug those into a stocking guide. Okay, not a whole lot of those out there. And a couple of things you want to be aware of with these stocking guides is that the ones that are out there are typically for even aged. Okay, and so it's making management decisions for even aged management. All right, and of course this is for hardwoods. It's essentially the same one that we use in the Southern Appalachians as well. We do find out, and I hope you remember, that this really only works for hardwoods that are in kind of our medium sort of sites. We've gone out and tried to use these things on yellow poplar, and yellow poplar usually just goes through the roof on it, and which it ends up estimating yellow poplar as being overstocked. And so the yellow poplar has every right to be up over here. It's not that the yellow poplar is growing wrong or that this chart is wrong. It's just that this chart is designed primarily for relatively less productive sites, and also for species that are not capable of growing in as dense a stands as some of our southern Appalachian yellow poplar does. Okay, so just bear that in mind. That when you're doing that on a good site for yellow poplar, you're going to end up over in that overstock section there. It doesn't mean that you can't use this guide. It just means that what they're saying is overstock is not necessarily overstock for yellow poplar. Okay. So, like I said, the book then goes into some of the economic evaluation of natural resources, and we will be spending a little bit of time later on going through some of these things. Okay, and they are basically using financial formulas to see what the current value of some management activity might be and what the future value of that activity might yield. So that's kind of cool. I jump into I just have here the questions, and there were a couple of questions that you are required to do. I don't recall which ones they are right offhand, but they are in there. So that brings us into chapter 4, where again, chapter 4 is really focuses on these things called estimation and projection of stand and forest conditions. So this really talks about growth models and those sorts of things. But in order to be able to identify what growth models are out there and how these things work, how we model future stand conditions, you have to know something about the current stand conditions and how they're growing. So it spends a little bit of time talking about the differences between even-aged and uneven-aged stands and how we use those some of the estimates that we have out there as guides for making our management decisions. So that's really what this is going to be about. So we're going to take a look at the growth of forests in this. And then later on, we'll tap a little bit into conceptual models, broad scale forest transitions, volume and yield tables. Those are pretty important. We already know what volume tables are. We've used those. Yield tables allow us to project into the future. And then also there are these more formal high-tech growth and yield models and growth simulators that are out there. And we'll play a little bit with those, but we don't get too worked up over them. There's not very many consulting foresters out there who spend a lot of time with these growth and yield simulators. It's just they're nice for management if you're working for a very high-tech company that is doing large-scale forest management for folks. It is good to know that they're out there, and we will explore them a little bit, but just not in great detail. So this chapter starts off with some important terms and definitions that we use when we're talking about growth and yield and projections of how forests grow. Allow us to describe how some of the things that are in place, some of these important dynamic things that take place in the stand. So some of the terms that they use that you'll hear a lot when you're seeing growth modeling and those sorts of things are the idea of ingrowth, increment, and mortality. Okay, these are three things that constantly occur, and more or less to some degree in any stand, and they have to be understood and kind of modeled for. So ingrowth is basically just saying usually you have a lower end, a lower diameter class that is usually where you start looking at the trees. And a lot of growth and yield models, they'll start that at 5 inches diameter. Okay, so before that, they're not really that interested in the smaller stuff. Some models go all the way down to like 1 inch and stuff like that. But typically, ingrowth means that it has the stems were there, but they were not really accounted for in the model, and then all of a sudden they've reached this point in their diameter class where they all of a sudden become of interest in that model. Okay, so ingrowth is usually something that you'll go out to a stand and you'll measure all the stems that are out there when you're doing like a permanent plot, or you go back and you repeat your measurements every 10 years, and you may have a whole pile of trees that were not in that stand, but now all of a sudden they're in there because they've kicked into that 5 inch diameter class. So they would be referred to as ingrowth trees. Okay, the trees that are still alive while you go back out there and measure at both ends of some sort of period of time. Let's say again it's a permanent plot. How much that tree has grown over that period of time is what we call increment. Of course, it's the same term that we use for the increment bore. So it's basically how much volume a tree has put on over time. Okay, so then we also have a couple of things that could have taken place to those trees. We could have gone back there and either there's no tree there, it's just a stump, and so that tree might have been harvested. Could have been firewood, could have been a thinning operation, but there was a tree last time you were there, and now there's not. So you've got trees that were harvested in between, and then you also have at the end of that time period when you go back out and remeasure, the tree may still be standing there, but it's dead, or it may have fallen over and it's dead. So you have mortality. So you have all these dynamic things taking place. You have trees that are moving into the system, trees that are checking out of the system, trees that had somebody check them out for them, and then those that survive and are continuing to grow, how fast they seem to be growing. Okay, and of course all those things are going to change over time. So he spends a little bit of time talking about on an even-aged stand this idea of competition resulting mortality can be envisioned using this thing he calls the negative two-thirds rule, or negative two-thirds power rule for self-thinning. And it's basically because it's used as an exponent on this equation here. We're not going to get into all that, but I just want you to kind of see what it's talking about here is for any given even age stand, you have these, you would start off over here with lots and lots and lots of trees per acre when that stand is young, and you would have relatively low average tree volumes, okay, in terms of cubic feet. So you got a lot of small trees. Well, they're growing like, like wild, okay? And so those trees are growing and growing and growing, and after a while, crown closure occurs, and so we start getting into our stem exclusion stage, and it can be defined as this line right here, this dotted line, where all of a sudden now some trees are going to start dying back, okay? You do have a bunch of winners though, and they're still growing really fast. The relative density of that stand, in other words, think about it in terms of light making its way down to the forest floor. If the stand is only 60% dense, that means that 40% of that light is still making its way to the forest floor. In other words, those trees still have a lot of room to grow, all right? Eventually they are, but as they start closing off, so I jumped the gun on it. This line right here is not crown closure. Crown closure is up here at the 1, okay, when it's 100%. So what's going on here, though, is trees are getting shaded out, and so the opportunity for mortality starts to begin right about here. And as the trees keep growing and becoming more and more dense, they're putting on more wood, but now all of a sudden they've reached this ceiling. It cannot get any more dense than this. And for a particular tree species, that could be light, that could be basal area, however you want to define it. But it starts to curve now, all right? And it starts following this pattern where the density will never get any higher than this. Trees will be dying back because you're moving from, let's say, 900 trees per acre to, by the end of this trajectory, it's at 300 trees per acre, but you got a lot of volume per tree, okay? So that's just a mortality curve that we see taking place based on the relative density of a stand. So that could be modeled using this, all right? So if you're a real egghead and you want to go ahead and develop your own model, you might follow some sort of a model like this. You could plug that into a spreadsheet, and it would actually come up with a value of how many trees per acre you might be able to see. So that's what growth modelers do, okay? And they're very useful. They really allow us to see, what might we expect to see on an even age stand as a result of just the self-thinning, okay? Trees just dying back due to natural mortality. So growth and management of even age stands are, again, a lot about this. We've already described it, and you can do extensive management where you don't do hardly anything to it. You harvest it and you let the trees just naturally regenerate, or you can get into all these other management, more intense ways of doing it. But the bottom line is you're starting at year 0 for the stand, and then you're growing it to some ending rotation. And that could actually be described in a chart that looks very similar to this here. So here's year 0. We don't have any trees growing. And then all of a sudden, trees they're planted and they're starting to develop, and we start putting on volume per acre. And in this case, they're looking at tons per acre. They're going to grow those trees to a certain time period, what they call the rotation age, as you know. In this case, it's a 45-year rotation age. And so as the trees are growing, the volume's getting up and increasing. It may reach a point where they are somewhere on this chart where they're thinking, okay, I'm going to have natural mortality. I may want to go ahead and knock back some of these stems and get the volume per acre. The volume per acre will drop pretty quickly, but it's going to bounce back. So this is what a lot of even age stand management looks like if you're plotting it out on a time scale. So in this case, all they do is one thinning at about year, I don't know, 22, somewhere around there, about halfway through the rotation. And then they let the trees grow until they reach the final harvest. And you can add up all the volume underneath this curve and see what your total volume is that you're getting off of. Of course, this first thinning, that volume right here, the majority of it's going to just be pulpwood. Final harvest, the majority of that volume is going to be saw timber. So there's going to be different values you would attach to these. But it is kind of a neat thing to take a look at and say, oh yeah, is this method going to give me better results than this method? Okay, so this method, I essentially am still going for a 45-year rotation, but I start at year 45 and I end at year 90. Okay, and in this case, I do two thinnings. I thin back at about, it looks like about halfway through, about 22 years or so. And then I come back at maybe 32, 33 years and thin it again. And these trees, even though I don't have, this looks like you have a lot more material out here. And you may end up, if I added up everything under this curve and compare it against the area under this curve, this may be a larger number, but this stuff is going to be of much higher value. All right, so adding it all up and saying, okay, this thinning here, I've got a lot of pulpwood here. Here I may have some chip and saw, and over here I've got some really high value timber. And if I added up all the money, it may turn out that this method pays better on that 45-year rotation than this method. Or it may be based on the productivity of the site that I don't do anything. I just let it all grow and then harvest it. So there's a lot of different ways of doing it, but they're really good ways of kind of identifying how you're going to be doing these sorts of things. Okay, so on the flip side, you may be wanting to look at it in terms of habitat quality. So year 0, I don't have much out there in terms of trees, right? But it may be excellent herbaceous forage. So that's at like the top of its game right there, okay? Right after you harvest and you regenerate, getting your new stand regenerated. And as time goes by, that habitat, the herbaceous species, and as you well know, they start to thin out and disappear as they get shaded out, okay? If you do a first thinning, you open that up again and you get some herbaceous habitat. So that's a way of looking at herbaceous habitat over time. Or you may be looking at the flip side of that, and that may be woodpecker habitat, because of course woodpeckers are looking for trees to peck at, right? And get the little bugs, the bark, and or they may be requiring some dead trees out there as well. So that's something to kind of keep in mind too. So as the herbaceous forage habitat starts to dwindle, your woodpecker habitat may be increasing over time. So again, that's just something to bear in mind when you're talking to landowners about the various things that are taking place and the dynamics that take place out on their stands. So Bettinger then gets into just a real quick and dirty comparison between the growth and development characteristics that you experience between even-aged versus uneven-aged stands. And so these are some of the metrics that we actually use, such as trees per acre, the mortality that takes place, canopy height, canopy cover, tree diameter, diameter distribution, basal area, timber growth rate, and timber yield. Okay, so and these are all can be described more or less by these curves. Okay, again, we're looking at even age stand curves here. Uneven age stand curves, development curves look similar to this. Okay, let me interpret this really quickly for you, and we'll get to it. Now, of course, you go, where's that reverse J-shaped curve? Well, that's a diameter distribution of an uneven age stand. What we're looking at here is the volume that an uneven age stand puts on and what the land manager is looking for over time. So what we're seeing, this dotted line here, that's the amount of growing stock level that it never goes below. In other words, no matter what you do out there, you have this volume of timber that you never go below. Okay? And it may change. It's not like you're saying there's certain trees I'm never going to cut. That's not what you're saying. You're going to go in there and you're going to cut every single tree over time, but that volume is maintained throughout the stand. Okay? And what you're doing is, as that volume increases over time, you're going to go in there periodically, say every 10 years. In this case, it looks like every 22 years. And you're going to do what's called entries, stand entries, okay? And that's what we talk about when this may be in 22 years, you go in and you do a group selection. And not only are you doing the group selection, but you're also doing some thinning in other areas as well. So you have some areas that you're doing group selections for the sole purpose of regenerating it, right? Remember, that's why we do harvests, is to regenerate. So you're cutting some trees for the purpose of getting a new stand established on those sites, but then you're also doing some thinning operations, or as we call them, intermediate operations, that are done for the purposes of benefiting the trees you've left behind, okay? But all together, all added up, you're removing a certain volume. So that volume over time is growing, and then you knock it back to what your reserved level is, okay? So again, you're never going to go below this. So what this develops are these series of entries that allows me to do various cuts. And the term that we call that, and we're going to get into this a little bit more detailed later on, we call those cutting levels, okay? And so we call them allowable cuts. And so on an uneven age stand, where you're trying to treat the whole stand or one stand of timber as an uneven aged unit, you have these allowable cuts that never allow it to go any lower than what you want as your reserve, okay? And you just go back and you just taking a little off the top, okay? So that's that's the way that a lot of folks cut their hair, right? They let it grow a little bit, or it could be the Nash and more recently James method of letting the hair get long and then all of a sudden schlocking it all and then growing it again and schlocking it all. Okay, which would be more the even age stand. And so you have these rotations where you remove everything. And of course, the reason we're doing this is because we're trying to manage for certain types of species. In the even age stand management, we're looking to manage, the shade intolerance, the shade tolerance to intermediates and intolerant, as opposed to even age stand management, where we're going for the shade intolerant species. Okay. Again, a lot of this is review for you all, but it's just you kind of hopefully you see what's going on a conceptual basis with that. So those two methods, various methods, where you remove everything, as opposed to removing just a little off the top and leaving this behind, is going to have different ramifications in terms of these growth and development characteristics. So, trees per acre decreases through time. Uneven age stand management, as you might guess, you have that's going to vary through time. So as the numbers of trees per acre start to increase as a result of a group selection, they're eventually going to be thinned out. And so that varies through time. The mortality of the stems, basically in an even age management, it hits that natural thinning line that we were just looking at before, and it starts, this natural mortality starts to take place. So at first it's pretty large, and then it starts to decrease over time. Whereas uneven age stand management stays relatively constant over time because you're always growing it to the same levels of mortality and then knocking them back. So height of the canopy, again, just like with with the even age stand, it's going to increase, it plateaus out, and then you harvest and you remove it all. But this will stay relatively constant over time on the even age stand. Okay, so again, you can kind of see what's going on with this is that you end up with these really different dynamics of the stand characteristics as a result of these two. Okay, and so I'm not going to you can spend time reading through that. And but what I did want to do is get into, so here again, we're looking at it from that flip side here, where you have the various habitat developments. Okay, so the herbaceous forage may be really good. It's never that right at that 100% excellent for the whole stand, but certain parts of that stand are going to benefit as you open up certain areas. So here, you only get enough sunlight that it reaches, the quality rating of 20% of what its full potential could be. All right, and that's taken across the whole stand. That increases over time, and then you pick, 22 years later, you're picking another area where you are removing trees and you're increasing the herbaceous forage for those areas. And again, so you can kind of see you end up with these smaller peaks where you're basically just throughout the life of that uneven age stand, you're just opening these different areas up. Woodpecker habitat's basically doing the same thing. So as areas start to close, you start to get woodpecker habitat. As areas start to open, overall your woodpecker habitat starts to decrease a little bit. Okay. So the other thing that I wanted to get into, what we start to describe in terms of management for uneven age stand, is this idea of this reverse J-shaped curve. Okay, this is the diameter distribution. So this is what it looks like. These are the trees per acre of the 2-inch trees, the 3-inch trees, the 4-inch trees, 5-inch trees, 6. Okay, you get the idea. What they're doing is they're just showing you here how you could actually break that up into the various different species. So these are Ostrea virginiana. A whole lot of those in the understory. Okay. There's some oak in the understory. This is Quercus alba, and so there's some oak in the understory, and then you also have this wide variety of all these other different species. Okay, so this is an uneven age stand deciduous forest in Georgia. The thing that's important to note is this is the curve that you see out there from direct data. Okay, we may be wanting to develop a curve that follows some sort of planned diameter distribution that we think is important for the best way of managing our particular stand. As you can see, a reverse J-shaped curve could be any one of these shapes, all right? And they all have different results in terms of how things get managed. So the important thing to remember is that what you're trying to do is to result in a curve or harvesting a series of harvests that are either going to be annual or periodical, that will serve the purpose that you want for maintaining certain types of timber and habitats, but that it stays balanced. Okay, so a balanced uneven aged forest is one at which the current growth, and that's what you're looking at, how much wood is being put on each year, can be removed annually or periodically while maintaining that same level, or while maintaining at the same time the structure and initial volume of the forest. Again, so trying to follow something that does this. Okay, and how that may be done is by looking at the volume for the various tree species that you have out there. So if I added up the volume of this is trees per acre, But what if I added up the volume of all these trees? All right. Here I've got a whole bunch of itsy bitsy little teeny weeny trees. Okay. And here I've got less of those, and you can see the blue line goes higher on track 27, gets a little bit higher than the orange one. So I have actually more larger stems out there. So here I've got relatively few small stems, and relatively large number of larger stems. Here I've got a whole pile of really teeny tiny trees, and as the diameters get bigger, it almost bottoms out to zero. Okay, so what is it that you are looking for? That's the most important thing. All right, so I've got a what defines this curve is what somebody, and I'm sure it was French, it was Delacourt, the law of Delacourt. Some folks call it Delacourt's Q, and some folks call it the diminution quotient, diminutive. Okay, in other words, it's the death curve, and what shape is that curve? So this quotient, or what they call it, the Q value, is basically a quotient that goes up in here. It's what numbers are you going to be attaching up in here, and that defines this Q quotient. Well, the Q quotient looks pretty complex and esoteric and way too abstract to be messing around with, but it's essentially, it's not that bad to think about. Basically, what we end up looking at are these quotients that are like somewhere around 1.5 to 1.2, somewhere in that. And basically all these are saying is that if I looked at one age class of trees, all right, and then looked at the next age class of trees and divided one by the other, the difference, the ratio would be that, the Q quotient. Okay, so in other words, so for instance, if I have 110 stems in the 1-inch diameter class, maybe up over here, the 1-inch diameter class, and then I look at the number of stems in the 2-inch diameter class, and it turns out there's only 88. So basically all I'm doing is taking that 110 and dividing it by 88, and that's the Q. Okay, so once you figure out what Q you want to work with, and it does range from what that does is it actually dictates what the shape of that curve is going to be. So a 1.5 curve would look like this. It's really steep. You lose a lot each year. A 1.2 curve might look like this, where you don't lose as much. I shouldn't say year, but you don't lose as many stems per acre when you're moving into the next diameter class. Which basically, moving into the next diameter class is the same as saying older trees. Okay, so that, again, that's using diameter class as a surrogate for age. So that's all they're doing with these things. They're developing these curves that fit developing these curves that have a shape that fit what they think is going to give them the proper balance, okay, for their management. All right, it seems really complex. It's really not that difficult. I think I've taken this data. I'm trying to remember. I've got it. I'm going to pull that up, and we'll go through an example of it. Okay. Okay, so here's an example. All right, I go out and I actually measure the diameters of a bunch of trees. I do a whole bunch of samples out there in this, and what I'm considering to be an uneven age stand of trees. And so for every diameter class, from 1 all the way up to the largest diameter class that I've measured out there, which in this case happens to be 29 inches, I've estimated how many trees per acre there are. Okay, how do we do that? 10th acre plots or whatever. Okay, and we just break it all up into the various trees per acre that we have based on our observations. So in this case, we see 1.78. We got 78 1-inch trees per acre, 63 2-inch trees per acre, 32 3-inch trees per acre. You see that number's going down, right? I mean, sometimes it pops back up again, but then it seems to be on this kind of, again, reverse J-shaped curve. What's our total trees per acre? We've got about 390 trees per acre out there. Okay, so plotting that out, that's actually this blue line right here. So it's kind of following the reverse J-shaped curve that that I would like to have based on just the research that I've been working on, and not me personally, but this is my for instance of my scenario, that just based on what I see other people doing, I may actually be more interested in having what I would consider a balanced curve that looks like this one here. Okay, what makes this curve balanced? Well, it's got the number of new recruits, the younger stems, where I want it to be, and I want it to end at, let's say, I probably want, what did I do? I actually made a cutoff. I think I may actually want to create a cutoff at a smaller diameter class. And I think I did in this case. I said I only want it to be 24 inches. So that was the largest. Notice there's nothing but zeros after that. So I basically am saying I only want this to go to 25 inch, about 24, 25 inches. So somewhere right around here. Okay. And so what you end up doing with this, and I want to end up with more or less about 200 trees per acre. Okay, so that's kind of the game you're playing. You go, how many small stems do I want out there per acre? What's the largest diameter class I want it to go to? And more or less, how many trees per acre am I looking for? And then, so you basically start playing around with these various Q values. So let's say I decided that 100 trees per acre is what I want for my my lowest diameter class. So I just plug that in there, right? And then I just start using different Q quotients, okay? So I know I got 100 here, and so how many 2-inch trees am I going to have? All right, so basically I'm just taking this number and dividing it by that Q quotient at 1.27. So basically this ends up being 27% of that number. This number does the same thing. This is 27% of that number right there. Okay, so each subsequent diameter class that I'm moving into, it gets reduced by 27%. I mean, that's all it's doing, okay? And what it ends up with is a desired curve that looks like this here, all right? So if I actually looked at what the true Q was, basically, in other words, if I took 75 and divided it into 63, this is 24% of that, okay? And so that's basically what we're saying, okay? And or this has got 24% removed, all right? And then I'm almost down, almost 50% here because I have a really high Q value for there. But that's just that's just the actual curve. So that's why it drops down really fast, and then it bumps up, and then it starts going back down again. But what you can see immediately is I developed this curve. I just threw this in there to kind of see what it looks like. This is the original curve, or that's what's out there. This is what I would like it to be. This is the current basal area of all those stems based on that. So basically it's just 78. Well, here I'll show you the formula. It's just 0.005454 times d squared. That's d, so I square that. Okay, so 1 squared times 0.005454, and then I multiply that by the trees per acre. So that's the basal area right now for the 1-inch class. Okay, what this is what this desired reverse J-shaped curve would end up with is a basal area of 0.5 square feet per acre of the 1-inch classes. Okay, so slightly higher in the 2-inch classes, considerably higher in all these other classes here. There's less trees, but they're well, in this case, there's more trees. Okay, yeah. So, but anyway, so what you end up with is essentially are these two stems, or these two groups of or two curves that describe what my actual stand distribution looks like and what my desired stand distribution looks like under my balanced system. So what I do is I start looking at differences between these. So here is an area where I need to get more trees per acre. Okay, so I need to recruit more trees. Here I need to take some trees out because they're above my desired curve. Here's another area where I need to start recruiting trees into this diameter class. And then here's an area where I can start removing things. Okay, so the best way of kind of thinking about it, why I created these basal area tables, is because I found that from the 11 to 15-inch diameter classes, in other words, from the 11 to the 15-inch diameter classes, I've got more basal area than I want. So how much should I remove? Well, I just take this area. So this is the actual basal area. That's my desired basal area. So I need to remove this much basal area, right, in those diameter classes. So that gives me a guide now. I need to remove about 6 square feet per acre of the 11-inch diameter classes. I need to remove about 8 square feet per acre of the 12-inch diameter class. Okay, so again, it's just a matter of going out and marking your timber that way. So you see, what a good guide this is in terms of telling you specifically by diameter class what needs to be done in terms of basal area removal. Right? So that's really what I wanted you to see, is that why these Q quotients are really important is you plot your desired one against your current one and use that as a guide to help determine how you're going to get there. Okay, and of course in this case this red line should really stop right about here because I don't want to go any higher than 24 inches on this. So everything above that 24 inches is fair game for me to remove. So that may or may not give me a lot of good, fairly meaty material that might get some work done out there, enticing loggers to come in there and do the work. Okay. So I took about an hour of your time out here. I guess it's better than me lecturing for 2 hours straight, right? So go ahead and answer those questions that are in the homework assignment, and I will probably by Monday. We'll have developed a short quiz based on some of this information as well. I think it's important enough that you know at least functionally how these things, why we have them, if not necessarily, I'm not going to make you recreate a curve for me, although I think it would be really kind of cool for you to be able to do that, but we're not going to go there. I just want you to know why we do these things and how they're done, okay? Especially the diminution curve. Okay, all right, so have a great week. See you Thursday.